Hello, everyone. Welcome to the second Lightning Talk. Today, I'll be talking about a project I've been working on, which is in relation to applying reinforcement learning to power ranking systems. So my name is Mehdi, and I'm an engineer at the Advanced Technology Group at Pinterest. I also have Jay Adams with me, who is from the Pinners Group and Signal team, who worked with me on this project. And we're happy to share with you some of our novelties and innovations. So Pinterest is a platform where users come to get inspired and find ways to act on their inspiration. So that makes Pinterest a different platform than other social media platforms such as Facebook, Instagram, and Snapchat, where usually people go there to share updates, photos, or videos. Usually when a user joins Pinterest, they have a problem to solve. Either they need to know how to decorate their room, find things to do in a city, or pick what to wear. As a result, one of our core objectives at Pinterest is to help them guide them through that journey going from inspiration to realization. So I thought of starting with a use case to make that more concrete. Let's take an example of this fictional character, which is Sarah. Sarah is planning a trip to Greece next summer, and she doesn't really know what she will be doing there. So she opens Pinterest and she wants to be inspired to know what to do there and maybe find ways to act on it. Sarah is a Pinterest user, so we have information about what she has been doing in the app, what boards she has, what pins she saved, and so on. So let's say Sarah likes islands and she likes water activities. So for that, we look at our billions of pins and then we filter them to a set of relevant pins that we think are appropriate for Sarah in this case. So here we picked, for example, some blogs about Santorini, some about Greece in general, and maybe some about activities such as a boat trip. So an ideal situation or scenario is to drive Sarah through that journey, because when she opened the app, she didn't really know what to do. So maybe we start with high-level information about Greece, such as this blog that shows general things about Greece. Next, we go deep and show her things about one of the Greek islands that is most usually traveled to by tourists, such as Santorini. Then an activity, such as a catamaran trip here. And then hopefully, if this is what she wants to do, maybe she will be inspired by that and then go and book her catamaran tour during her trip. So this is like an end-to-end solution from inspiration to realization. However, the reality, like most ranking systems do not work like that. Most of them do not treat the problem as a sequential problem. And one of the reasons why it's the case, because they rely on the common top K ranking method, where every item or every possible recommendation will have a score. And that score most of the time is an aggregation of some prediction on some short-term user feedback or user reactions to the pin. An example to that is whether the user will click on the pin, whether they will save it, like it, and so on. So the result of that system is you end up with a lot of recommendations that tend to be similar to each other, and also the order of the items is not really considered once it's returned to the user. And then finally, the system doesn't really try to solve a goal that the user came to with. The aim is to show highly relevant and interesting content, but not necessarily will drive the users through that journey. So that's what our team was thinking of, is how can we build that ideal experience for Sarah here? And what type of methods can we use when it comes to machine learning to do that? And that's where we thought of reinforcement learning. Can reinforcement learning improve that system? So what is reinforcement learning? Reinforcement learning is an RL, it's a machine learning branch that focus on developing algorithm and techniques for autonomous agents to learn how to make decisions to optimize some goals, some long-term goals. So usually agents are concerned with environment where there is that sequential interactions, where the agent needs to take a series of action in order to reach that final goal. And most of the time, these agents learn by trial and error. So because there is no ground truth that tells us what is the right sequence of action in order to reach that goal, the agent has to learn how to try different actions, and from that, it will learn those optimal ones that will satisfy the user. For our use case here for Sarah, we thought of having the agent take actions in the level of the pins. So the actions that the agent will be taking will be, the agent will be selecting the individual pins to show to the user. And the user here is the environment, because the agent will be interacting with the user. And every time the agent will be making a recommendation to the user will look at it, and their state will change. And also the user will give us a reward. And the reward is a signal to tell us how good the recommendation was. And here, like, the agent will be taking that reward. When it comes to the user representation here, we are using Pinner Sage, which is the user embedding, in addition to the user actions that the user took in the last while. So such as, for example, if the user liked some pins or saved them, so those are taken into consideration by the agent before taking an action. And then the final goal here of the agent is to learn a policy, which is a mapping between a state and an action. And that policy, the objective is to take an action that allows us to maximize the cumulative reward that the environment will give. When it comes to the algorithm used, we decided to use DQN, which is a value-based RL algorithm. And then this DQN, the objective of it is to learn an estimate of the cumulative reward of when taking an action given a state. So the expected cumulative reward is, we try to learn it by computing this total reward that we'd accumulate by taking an action. And that total reward is the discounted sum of all rewards after taking an action. And here, like, the assumption is that that same agent, not only it will take an action now, but it will keep taking the next several actions. And here the actions are selecting which pin to recommend to the user. And then once we have a good Q network or estimator of this long-term value of taking action, we can infer a policy from it. And the policy here can be greedy, where given a state and the set of actions, we would pick the best action from them based on how much reward that action would lead to. And of course, like in reinforcement learning, we need to do some exploration and exploitation. And then in this case, we can do epsilon greedy exploration, or we can do some softmax exploration. When it comes to training this DQN, the actual training method is fairly similar to the common ranking models. So we have a neural network that takes in features that represent both the state of the user and some feature representation of the pins that we're trying to estimate. And then the output would be a score. And here the output is the estimate of the long-term reward after taking that pin. So in order to train this model, we need the data to be in the format that I added on top right, which is an state, action, reward, and next state. So that is a transition. And that is how we will be computing the target. So what is the target Q value that we are trying to optimize the model towards? And that target is important to compute the loss. DQN computes the target by adding the direct reward from that experience that we have. So given it user state and action, we use that direct reward plus an estimate of the next state. And the estimate of the next state, the value of the next state, is by doing an argmax on what's the best state we can be by taking the next action. So given the target, and we have a predicted value that the model currently predicts, that's how we compute the error. And then the Q loss is inferred from it. And then this is a loss that will be used in order to do the model training, so that we can improve the estimation of this model to get closer and closer to those targets. When it comes to the training paradigm, because I just showed you how the GQN is trained, but in reinforcement learning, we don't have a static data set that the agent will be learning on. So the agent here in this experiment, the agent will be learning by interacting with the environment, and it needs to do the trial and error. It needs to do some exploration because we don't know what's the best solution. So the training paradigm is composed of these two different components. There is an agent trainer in the left, and then an environment on the right. So I'm going to start with the agent trainer. So the agent trainer first receives that experience that we were looking at earlier, that SARS, and it's added to a replay buffer. A replay buffer is a data store that contains all those experiences, from which we'll be sampling mini batches of experiences so that we can improve the Q function. And then once the Q function is improved by doing some training, we can infer a policy from it. And the policy will be selecting a certain number of, some percentage of the time, the best action available, and some other time it will do exploration. Once that action is taken, it's applied on the environment. And that's the environment on the right. So the environment will receive the action, and the objective is, given that action, the environment will change the state and will compute a reward and give it back to the agent trainer. There are two ways we can set up this environment. One way is to use the real users as an environment and have the agent take the actions on our online system. And then based on that, we see what the next state is and what the reward was. The other solution is to simulate the user. So instead of interacting directly with the real user, we can simulate the user so that we can do that offline exploration and agent learning without impacting our real user. And that's what we end up going with. So we built a user simulator that, given an action, an initial state, it will do the state transition, it will generate a reward, which it will give back to the agent trainer. One of the challenges with training the agent using this setup is the scale that we deal with. So at Pinterest, we have over 400 million monthly users, and we have billions of pins. So that means that we'll need to simulate these at scale. And this paradigm that I have shown has coupling between these two steps, which can slow it down. So it quickly became a bottleneck for training. And that's what made us transition to this new training paradigm, where we decoupled the data generation from the learning. So on the left, we have a set of actors or workers, and those workers, their main job is to generate data or generate that SARS tuple, which has the experiences that we are going to learn from. So these will keep continuously working, generating these transitions. They're added to a queue. Once a queue reaches a given size, it will be sent to the learner, to the replay buffer. And the learner on the other side is always training, is always using experiences from the replay buffer to improve. So these are in some ways decoupled. The only thing is that the learner, as it's training the GQN model, it will be broadcasting and sending back a new snapshot of its model to the actors so that they can continuously generate with a newer version of the model. So this design made the system a bit off policy because the generation is done using a policy different than the one being trained because of kind of how they work independently of each other. But then that improved the speed at which we can generate these experiences and the speed at which we can train, because none of them is waiting for each other now. So that improved the conversion speed by several orders of magnitude. It also allowed us to have finer control over the resources that are used by each of these steps. Because, for example, the learner might need more GPUs, but the transition generators or actors might need more CPUs. By having them working, like running on two different systems, that allowed us to easily customize the resources used and scale them appropriately. So given this training process, we end up training an agent for one of our surfaces in which we show users videos, and then the user can navigate across between those videos. And our objective was to test to see if this agent is able to optimize over the user's long-term session instead of just directly giving them the items they're looking for. So for offline evaluation, we use a simulator to do that offline evaluation. So we have two policies or two models. One of them that was the RL model, and the second one is the control. The control is a greedy model that always selects the best action based on the short-term score. So when we compared them, we saw that the RL model does indeed improve the two of the main metrics we care about, which are here, how long the user watched, the actual items that we recommend to them, and in addition to how many items will the user watch during their session. So the first one increased by 10%, the second one increased by 11%. And these are generated using the simulator offline. So given these positive results, we end up running it on a line system, and then we saw a slight decrease in those metrics, but it's still directionally correct, where we have a plus 8% in that watch time and plus 5% in the session length. So I thought of sharing with you some of the learnings from this project. One of them is that simulators can be useful for this training agents offline and evaluating them. Simulators, they don't need to be perfect. And in our case, they were very useful when it comes to solving our problem, our cold start problem, and also exploration. Second is the importance of streamlining this training process at scale. Setting up the tooling and infrastructure to do the RL training offline was challenging, but definitely building the frameworks and tooling to allow us to reuse it was allowed us to move faster at prototyping and experimentation. And then finally, the DQN architecture is fairly straightforward to deploy and run when it comes to ranking because of its similarity with the interface of common ranking system. So the models take the same type of inputs, where input about features about the state, the user, and the items, and the output is a score. The only difference is the meaning of that score. One of them is a short-term value, the other one is a long-term. So as we reached the end of the presentation, I wanted to highlight the great potential of reinforcement learning when it comes to ranking systems. So through this work, we're able to add another dimension to the ranking system, which is time. And by considering the long-term impact of recommendation, we're able to be more thoughtful about the recommendation we're making. And instead of just maximizing over short-term engagement, we're thinking of long-term. And in the case of Sarah, the objective is to help her navigate that problem that she had, which is going from inspiration to realization. Finally, I wanted to take a moment to thank the colleagues and all the team who worked on this project. Thank you, Jay, Kritarth, Yang, Vish, Jiajing, and Dhruval. And now I'm open for questions. All right. So question number, I'll read the questions and I'll answer. So how do you come up with a transition function in the user simulator, given that the dynamic of the environment could be very complicated? Yes, that's a good question. So in this case, what we end up doing is we train another model in a supervised learning way to predict user feedback to recommendations. So here, there are several feedback that we care about, which are part of that transition function. So we predict those, and that is what allows us to update the user state, and it also allows us to compute the reward.
I think, by the way, I think maybe the question too is like, what is the user state? And we just think of it as what has the user seen, right? So it's very simple. We're not trying to model like what's going on in the user's mind or anything like that.
Yeah. All right, I'll go to the second question. Second question is, how were you able to build a user simulator that behaves like a real user? I think that's a very similar to this question, which is by leveraging a model to do that transition.
it's really just a rank. It's like a ranking model. Ranking models,
Yep.
we have these multitask ranking models that say, what's the probability that the user will repin this thing? What's the probability that they'll watch it, that they'll save it or whatever? And so the ranking model is just the user simulator. It's just a model that tells us, if we were to show this to the user, what's the probability that they would take this or that action.
Yes. All right. Question number 3. Let's say that Sarah has saved and liked some pins on furniture decor whenever she uses Pinterest so far. The next week, she has a plan to go to Greece. Isn't the past of Sarah user more geared towards furniture? How would the DQN help in giving pins related to Greece? So that is up to the model, the DQN, to learn it. So when it's similar to the previous question, it all depends on what features we're giving to this model. So the model has access to 2 things. One of them is the user representation, which is a general representation of the user taste. And the second one is a large sequence of number of actions that the user took. So it will have actions in relation to the furniture and others that are not related. So the model needs to learn which features to focus on, and it will gear its optimization, like its recommendation on that.
Yeah, and by the way, the way it does that is we use a transformer to consume the recent actions of the user, and part of the attention signal of that transformer is, what is it that we're considering? So if we're considering a pin about Greece, we look at the history of recent actions and we say, which one of these have anything to do with travel? And that will give us a clue as to what to do about Greece.
Yeah, exactly.
I think
All
that
right.
we're at time.
Yeah, that's what I think. All right. Well, thank you very much. Have a good end of day.